Hi folks. We're going to look at how to solve literal equations for given variables. What do we mean by a literal equation? A literal equation has two or more variables. So if you just have one equation and it has two or more variables, you can't actually solve it and get a number answer. It cannot be solved for a number value. It can be rearranged, but it can't be solved for a number value. The most common types of literal equations that you're likely to come across are formulas. And formulas show how one variable is related to one or more other variables. Like, for instance, the formula for the area of a square or an area of a rectangle is the length times the width. So area equals length times width. I haven't given you any numbers there. I've just given you a bunch of variables. Area equals length times width. And you can't solve this for a number unless I actually give you 2 out of the 3 numbers. So it can be helpful to be able to take an equation like this and rearrange it in terms of the other variables. So maybe you don't want to know that area is length times width. Maybe you want to be able to calculate length. And so that's what we're looking at. How do you get length all by itself on one side of the equation and know that length is area divided by width? How do you take an equation like this and rearrange it to look like that? So that's what we're learning here today. The math skills we're learning here are the same that we've been using throughout this module. We're going to isolate the requested variable on one side of the equation by using reverse PEMDAS to kind of unwrap that present, unwrap the one variable that we're trying to focus on. So let's look at this example here. 3y plus 4x equals 9, and I'm supposed to solve this for y. I'm supposed to get y all by itself on one side of the equation. So to do that, first of all, to get y all by itself, I'm going to have to get rid of this x that's kind of attached to it. Remember, reverse PEMDAS, I want to focus on the addition subtraction that I'm getting rid of first. So the 3y is being added to the 4x. I'm going to want to subtract away that 4x from both sides of the equation. And I get that 3y, remember this 4x cancels out here, 3y equals 9 minus 4x. It is incredibly important when you're doing this to remember that you can only combine like terms. Negative 4x has an x as its last name, so it cannot be combined with 9, which does not have x as its last name. Like terms have the same last name, and they have to have the same last name in order to be added or subtracted from one another. So I cannot combine the 9 and the negative 4x, so I keep them both there separately. But what I can do is I can divide both sides by 3. When I divide by 3, I get y by itself on this side of the equation. But let's look at what I have here, because this is basically an example of the distributive property. That 3 is dividing the 9, but that 3 is also dividing the negative 4x. So what we're going to do here is we're going to say 9 divided by 3 is 3. But we're going to say negative 4x divided by 3 is just negative 4/3 x. And this is this is a good way to write the equation, is leaving it as 3 minus 4/3 x. Let's look at another example. Here, I want to solve for x. Right now, it's being solved for y. I don't want it solved for y. I want to solve it for x. I want to get x all by itself on one side of the equation. But if you notice, x appears twice in this equation. When that happens, when you have two terms that contain the variable you want to isolate, try to factor the variable out. Try to turn it, instead of this addition subtraction problem, turn it into a multiplication problem. So what I can do here is I can pull x out of both terms and say that I have 3 plus 5z. So I factored the x out, and I have x times 3 plus 5z. It's like the opposite of the distributive property. And all that together equals y. Now that I have that, now that I've factored out the x, I can easily get x by itself by dividing away this parenthetical expression that's multiplying it, that 3 plus 5z. And if I divide by 3 plus 5z on that side, I have to also divide by 3 plus 5z on this side. And we get as our final answer x equals y divided by 3 plus 5z. And you can leave that bottom expression in parentheses if you want to. But it's implied the way we wrote the fraction this way, that it's all beneath, it's all in the denominator. Let's try another example. Let's look at question C. So speed equals distance divided by time. Speed equals distance divided by time. This equation, or the problem says here, solve for d and solve for t. So let's solve for d first. To get d all by itself on one side of the equation, right now the d is being divided by t. So to get rid of t, I need to multiply both sides of the equation by t. And I get as my final answer that d equals t times s. D equals t times s. Now, how do I solve for time? For time, I need to get time all by itself on one side of the equation. But if you look at the original equation, time is in the denominator. Remember, you cannot solve for a variable unless it's up top, unless it's in the numerator. How do I get time into the numerator? The easiest way to do that is to just multiply both sides times time. Time divided by time is 1, and so multiplying or dividing by 1 doesn't do anything to the d, so we just have the value d on the right-hand side. And on the left-hand side, we have time times the speed. Remember, my goal is to get time all by itself, so I'm going to divide away the speed, because I don't want the speed there anymore. And I get that time is my distance divided by my speed. Let's do another example. The formula for the surface area of a rectangular prism. If I solve this for the length, I'm focusing on L, and I'll try to write that in cursive so it's a little easier to see that it's not the number 1. I want to have all my L's on one side of the equation. I've got L's here, I've got L's here, so I want to get rid of this thing here. So I'm going to subtract it away. I'm going to subtract away 2WH, subtract away 2WH, and I get that S minus 2WH equals my 2LW plus my 2LH. I promise to do that in cursive, like that. All right, I now have this situation mentioned before that if two terms contain this variable that I want to isolate, try to factor the variable out. So that's what I want to do. I want to pull L out of here and pull L out of here by doing the reverse distributive property. So L I've pulled out of the expression, but I have 2W plus 2H left. And on this side I have S minus 2WD. It's now easy to get L all by itself by dividing both sides by 2W plus 2H. Divide both sides by 2W plus 2H. And you get as your final answer that L equals S minus 2WD over 2W plus 2H. Lastly, one that might be more familiar to you and you can see the value of it more readily is converting between Celsius and Fahrenheit. This is the equation that lets you convert from, in this example, we're going from Fahrenheit. You plug in your value for Fahrenheit and it calculates Celsius for you. But what if we want to do the opposite? What if we want to know degrees Fahrenheit if we're given degrees Celsius? We can do that if we rearrange this equation to solve for F. So how do we do that? Let's reverse PEMDAS. Right now, there's no addition subtraction that we can easily access because it's inside parentheses. And remember, we're doing reverse PEMDAS, so I want to do addition, subtraction first, then multiplication, division, and save parentheses for last. So I'm going to focus on this 5/9 fraction here. I want to get rid of that multiplying by 5/9, and the best way to get rid of that is to multiply both sides by 9/5. Multiply by 9/5. So the 5/9 and the 9/5 when multiplied together just give you the value 1. So I'm left with 9/5 C equals F minus 32. Now I'm a lot closer to getting F all by itself. I can add 32 to both sides of the equation, and I get that F equals 9/5 C plus 32. And that is how you convert from degrees Fahrenheit. If you're given degrees Celsius, you can calculate your degrees Fahrenheit using this equation. I hope this helped.